Hello, Integrated Math 1. Welcome to lesson 1.2.1. We're doing it all in one today. So today we're going to be recognizing patterns and sequences. So just to kind of get us started, right? You guys know patterns and how they work. So just to kind of get your brain jump started and going, I would like you to take a look at our warm-ups here on page 83 and 1-83. And I'd like you to do two things. First, I would like you to write the next three terms in the pattern. And then I would like you to explain how you generated each term. So how'd you get those terms? Go ahead and hit pause to try these out and hit play when you're ready to check your work. So let's talk. If you were having a hard time with the first two, I would start thinking about a calendar, right? If you thought about a calendar, hopefully you realized these were the months of the year. This was January, February, March, April, May, June, July, August, September, which means the next three would be October, November, and December, O-N-D. These were totally the months of the year. And I also thought of a calendar when I looked at number 2, and I thought, hey, those are the days of the week, Sunday, Monday, Tuesday, Wednesday. So the next three would be Thursday, Friday, Saturday, TFS, because they are the days of the week. Hooray. This next one you probably didn't have too much trouble with. 5, 10, 15, 20. We're counting by fives. We're adding 5 each time. So 5, 5, 10, 15, 20. The next three terms would be 25, 30, 35. We're just adding 5 every time. You could have said count by fives as well, but I'm going to say add 5. It just feels a little more precise. Do you have a little trouble with this last one? It's actually not as bad as it seems. Hopefully you realized these were perfect squares. Did you catch that? Did you notice that? That this 100 is actually 10 squared, 81 is 9 squared, 64 is 8 squared, 49 is 7 squared. Did you catch that? Which means the next ones would be 6 squared, 5 squared, and 4 squared. So 36, 25, and 16. They were decreasing perfect squares. Yeah, that one was a little tricky, I will admit. But we've at least got our brain moving in the right direction now. So we are going to be recognizing patterns and sequences. We have several learning goals today, just recognizing and describing our patterns, right? Adding 5, days of the week, decreasing perfect squares. We're also going to represent our patterns as sequences. If you don't know what a sequence is, don't freak out. We will be talking about that. And predicting the next term in a sequence. You were already doing that with your warm-up, predicting what's going to come next. And we're going to take those terms and that sequence and we're going to represent it as a table of values. We're just going to put all of our information into one convenient, easy to use table. So we do have several key terms, including sequence. I did mention, don't panic if you don't know what a sequence is, we'll get there. Term of a sequence, infinite sequence, and finite sequence. These are our key terms today, so keep an eye out for those words in bold as we go along. So since early elementary school, you've been recognizing and writing patterns involving shapes, colors, letters, and numbers. How are patterns related to sequences, and how can sequences be represented as a table of values? I should warn you, as we go through today, we're not doing every single problem in this lesson, so we're going to be skipping around a bit. So make sure you're paying attention to those page numbers up in the corner so that you know where we're at. So for our getting started activity on page 84, we have a pyramid of patterns. This is Pascal's triangle. Pascal's triangle is a famous pattern named after the French mathematician and philosopher Blaise Pascal. And I probably pronounced that badly because my French is terrible. A portion of the pattern is shown. So here's a portion of the pattern. I would like just to start off, can you list at least 3 patterns that you notice? And maybe you notice more than 3, that's okay. Can you just list off any patterns that you notice about this triangle? Go ahead, hit pause, jot it down, hit play to keep going. So I noticed several things. I noticed that the sides had 1s all down them. Maybe you notice that too. I also noticed though that on the inside, like if I started with this 1 and I counted down, it's like 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. And I was like, that's so cool. So inside the ones, it counts from 2 to 6, which is awesome. So I thought that was interesting. But here's the really big thing I noticed. I noticed that each number is the sum of the two above it, right? 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 1 is 3. Oh, did you see that? 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. Do you see that? How we're getting the next row by adding the two numbers up above. 1 plus 4 is 5. 4 plus 6 is 10. 6 plus 4. 4 plus 1. Yep, you see it now, don't you? 1 plus 5. 5 plus 10. 10 plus 10 is 20. 10 plus 5. 5 plus 1. Ooh. Yeah, that's where these numbers are coming from. They're not random. They're coming from someplace in particular. So with that in mind, we're going to skip down to number 5. We're going to skip the ones in between, sorry. But we're going to skip down to number 5, and I would like you to determine the next 2 rows in Pascal's triangle. Go ahead and hit pause to find the next 2 rows now that you see the pattern, and then hit play when you're ready to check your work. So we said the pattern was to add them up. So I'm going to start with a 1, right? I'm going to start with a 1, and then I'm going to add these guys. 1 plus 6 is 7, and then I'm going to add these guys. 6 plus 5 is 21. You may want a calculator today, by the way. If I didn't mention that before, I'm sorry. You want a calculator today. Trust me. 15 plus 20 is, of course, 35. And then you'll notice it starts to repeat itself. 20 plus 15, 35. 15 plus 6 is 21. And then, of course, 6 plus 1 is 7. And we do put another 1 out on the end because we want to keep that ones on the outside pattern going. This is not very pretty, so I'm going to erase this, and I'm going to show you my little typed bit. There, that's so pretty. And of course, we need to do the next row. We were asked to do the next 2 rows. So 1 on the outside, and then 1 plus 7 is 8. 7 plus 21 is 28. 21 plus 35 is 56. 35 plus 35 is 70. 35 plus 7 is 50. That's not right. I missed a number. Oh my gosh, my 21. There should be a 21 in there. I'm putting a 21 in there. There's a 21 in there. 35 plus 21 is 56. 21 plus 7 is 28. 7 plus 1 is 8, and then a 1 on the end. Sorry, I lost my 21. My bad. We wrote it down earlier. We just lost it this time around. No big deal. We fixed it. Yay, us. So a sequence, if we flip over to page 85, here's some bold terms we should know. A sequence is a pattern involving an ordered arrangement of numbers, geometric figures, letters, or other objects. So when we're talking about a sequence, we're just talking about an ordered pattern. That's really all we're talking about. A term of a sequence is an individual number, figure, or letter in the sequence. So if I were to pick one item out of my sequence, that would be a term of the sequence. So examples of sequences are given in this following activity. There's actually 10 of them. We're only going to do 4. If you would like to do all 10, I won't stop you. But we're just going to stick with 4 of these, all right? And here's what you're going to do. For each of these sequences, and it walks you through A, B, C, D, all this stuff. For each sequence, first thing, part A, you're going to describe the pattern, okay? Part B, you're either going to draw the next terms or write what the next terms are. And for part C, you're then going to represent it numerically. And that is, you're just going to list it off as a set of numbers. And the last part you're going to do is you're going to put it all into a table. You'll see what I'm talking about. So let's go ahead and start off with number 1. Positive thinking. Look, they're all little plus signs. So I would like you to analyze the number of dots. So you're going to want to count up how many dots there are and describe the pattern. Go ahead and hit pause to describe it. Hit play to keep going. So I counted and I was like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. I was like, all right, we've got, and I'm going to make a little list here. We've got 25 dots here. But then each end got shorter by 4. So if you counted, this one only had 21 dots. And this one, oh, I took one off of each end there. So I lost another 4 dots. So I guess I'm now down to 17 dots. And then we took another one off of each end. So now we're down to only 13 dots. So the pattern, each figure has 4 fewer dots than the figure before it. Yep. So draw the next 3. Go ahead and hit pause. Draw the next 3 figures of the pattern, and then hit play to check your work. So for the next one, I took one off each end, and then the next one, I took another one off each end, and wow. And finally, I just had one lonely little dot left. It must have been lonely, probably. I would like you to represent the number of dots in each of the 7 figures as a numeric sequence. So go ahead and hit pause, and you're just going to list them off in order. Remember, a sequence is supposed to be in order. So we said there were how many dots, how many dots, how many dots, how many dots. Just list it off as a list of numbers. Go ahead and hit pause to write it down. Hit play to keep going. So we had already written down the first ones, right? 25, 21, 17, and 13, but we took off 4 more, so the next one was 9, took off 4 more for 5, and took off 4 more till we only had one lonely little dot left. So this is our sequence. This is our numeric sequence. You literally wrote your sequence as numbers, all right? That's a numeric sequence. No big deal. And last but not least, we're going to represent the number of dots in each of our first 7 figures as a function using a table of values. Remember, we can write functions as tables. We know this. So all you're going to do is fill it in. How many dots in your first term? How many dots in your second term? On and on and on. You're basically just taking your numeric sequence and plugging it into the table. That's all you're doing. So go ahead and hit pause to fill in your table and hit play to check your work. All right, so we said that the first term, this first cross here, had 25 dots. The second term had 21. The third term had 17. The fourth term had 13. The fifth term had 9. The sixth term only had 5. And the last term had 1 lonely little dot. It was a very lonely little dot. So you get the idea. So this is what we're doing for all of these problems today. And in fact, this is what you're doing for all of your homework tonight as well. Describe the pattern. List the next couple of terms. Give me the 6 terms in a sequence, right? Give me all the terms in a sequence and give me all those terms in a table. That's all we're doing. So with that in mind, I would like you to tackle number 4. We skipped all the way over to page 87. Sorry about that. Again, we're not doing all of these for the sake of time. We've gone all the way over to page 87, and I want you to do all of this. I want you to do parts A, B, C, D. I want you to do all of it because now you know how this works. So go ahead and hit pause to work your way through number 4, and then hit play when you're ready to check your work. So Al's house of eggs not makes omelets. I like omelets. Al begins each day with 150 eggs to make his famous Best Western omelets. After making 1 omelet, he has 144 eggs left. After making 2 omelets, he has 138 eggs left. After making 3 omelets, he has 132 eggs left. So it looks like the pattern is that Al has 6 fewer eggs after making each omelet. Those are big omelets. It's like 6 eggs in an omelet. That's amazing. I bet they're really good. Next up, determine the number of eggs left after Al makes the next 2 omelets. So 144. So we had 150, then 144, 138, 132. Ooh, but we're going to make 2 more omelets. So if we subtract 6 more, so after 4 omelets, he'll have 126 eggs. Subtract 6 more there. So after 5 omelets, he has 120 eggs. So many eggs. It sounds really good. Maybe I'm a little hungry. For part C, of course, we're going to do two things here. So for part C, we're going to represent the number of eggs left after Al makes each of the first 5 omelets as a numeric sequence, and then represent that sequence using a table of values. So we started off with 150, and then 144, 138, 132, 126, 120. And now, of course, we want to put it into our table. So first we had 150 eggs, and then after each omelet, we lost 6 eggs. And my table wasn't quite big enough, which annoyed me, so I made it a little longer. All right, let's skip to number 9. We're just jumping everywhere, aren't we? We're all the way over on page 91. We're just jumping all over the place. So page 91, let's talk about a pizza contest. This one's a little trickier, but again, you're going to describe the pattern. You're going to write the next terms in the sequence. Then you're going to write it out as a numeric, write all of them out as a numeric sequence. You're going to go ahead and put it all into a table. Go ahead and hit pause to work this out, and then hit play when you're ready to check your work. So Jacob is participating in a pizza making contest. Each contestant has to bake the largest and most delicious pizza they can. So much food today. Jacob's pizza has a 6 foot diameter. That means that pizza has a diameter that's my height. That's amazing. After the contest, he plans to cut the pizza so that he can pass the slices out to share. He begins with one whole pizza, his big old 6 foot pizza, and then he cuts it in half. After that, he cuts each of those slices in half. And then he cuts each of those slices in half, and so on. So think about the size of each slice in relation to the whole pizza. So this means the pattern is that after every cut, each slice is half the size of each slice in the previous cut. So we keep cutting things in half, right? Cut in half, cut in half, cut in half. So determine the size of each slice compared to the whole pizza after the next 2 cuts. All right. Hang on, I gotta make some notes here. So we started off with a whole pizza, and then he cuts it in half, so we're down to half. And then he cuts that in half again. Well, half of a half is a fourth. And then he cuts those slices in half. Oh my gosh. So he cuts those in half. So half of a fourth is an eighth. So that means the next cut, so we've cut 1, 2, 3 times. So on the fourth cut, half of 1/8 is 1/16. So we're down to 1/16 of the original pizza. And if we cut that in half again on our 5th cut, then that means we're down to 1/32. Half of 1/16 is 1/32. Oh my goodness. These are going to be some skinny slices. Long, skinny slices. 6 foot pizza. Oh my gosh. And of course, I'm sure you wrote this as a numeric sequence. So 1, 1/2, 1/4, 1/8, 1/16, 1/32. And then we put it into a table. So my first term was 1, my second term was 1/2, my third term was a fourth, and so on, and so on, and so on. Yay. That one was a tricky one. I know how much you guys love fractions, right? Next up, page 92, coin collecting. Go ahead and hit pause, answer all the questions, hit play to check your work. So Miranda's uncle collects rare coins. He recently purchased a rare coin for $5. He claims that the value of the coin will triple each year. Triple, that's 3 times, right? So even though the coin is currently worth $5, next year it will be worth $15, in 2 years it'll be worth $45, and in 3 years it'll be worth $135. So think about the value of the coin, how the value of the coin changes each year. Describe the pattern. The pattern is that each year the coin value is 3 times greater than its value the previous year. You probably figured that out from the triple thing. So after 3 years, we're at 135. You remember how I said you need a calculator? I would grab a calculator. So the value of the coin after 4 years, well, 135 times 3 would be $405 after 4 years. And after 5 years, well, $405 times 3 is $1,215. So we just kept multiplying by 3. So if we write that as a numeric sequence, we have 5, 15, 45, 135, 405, and 1,215. Again, this is why you want a calculator. I'm just saying, I don't want to do that in my head. Oh, and of course, put it in a table. So term 1 is 5, term 2 is 15, term 3 is 45, term 4 is 135. Well, I can't keep up. Term 5 is 405, and of course, term 6 is 1,215. Rock, rock on. So let's look a little more closely. There are many different patterns that can generate a sequence of numbers. So for example, you may have noticed that some of the sequences in the previous activity were generated by performing the same operation using a constant number. And in other sequences, you may have noticed a different pattern. The next term in a sequence is calculated by determining the pattern of the sequence and then using that pattern on the last known term of the sequence. So can you just take a look at the 4 activities that we did, the 4 sequences we did? We're on page 94. And again, we've skipped a little bit. But can you go back and look at the 4 that we worked on and tell me which sequences were similar and why? Go ahead and hit pause to write it down and then hit play when you're ready to check your work. So I noticed that some of my sequences were either increasing or decreasing by adding or subtracting. Did you notice that? Like I noticed that the positive thinking, we kept subtracting 4, right? And I also noticed that for Al's omelets, we kept subtracting 6. That was the pattern. But I noticed that some sequences were increasing or decreasing by multiplication or division, right? For the pizza contest, we kept cutting it in half, cut it in half, cut it in half. For the coin collecting, we kept multiply by 3, multiply by 3, multiply by 3, right? Now, we only did these 4. If you did some of the other sequences, which we didn't get to in this video, you may have noticed that some sequences may follow neither of those patterns, may have a totally different pattern altogether. But I think it's important that we notice that some of these sequences change by adding or subtraction, and that some of these sequences change by multiplication or division. And I hope you also notice that all of these sequences are functions. Every single one of them is a function. That's a thing. So, page 94, I'd like you to consider a sequence in which the first term is 64, and each term after that is calculated by dividing the previous term by 4. Margaret says that this sequence ends at 1 because there are no whole numbers that come after 1. So divide by 4, and Margaret's like, you got to 1, you're done. There's no more whole numbers. Jasmine disagrees and says that the sequence continues beyond 1. Who is correct? If Margaret is correct, explain why. If Jasmine is correct, predict the next 2 terms of the sequence. Go ahead and hit pause, jot down your thoughts, hit play when you're ready to keep the discussion going. So, guys, I hate to break it to you, but Jasmine is correct. Jasmine's right, because you can divide. It didn't say it had to be a whole number. You can keep going after 1. You can divide 1 by 4. 1 divided by 4 is 1/4. 1/4 divided by 4 is 1/16. So Jasmine was right, and the next terms are 1/4 and 1/16. Wasn't done yet. Still more to go. And this brings us to a couple of more terms. So we have 2 more terms here for you guys. If a sequence continues on forever, it's called an infinite sequence. We can divide by 4 forever and ever and ever. It's an infinite sequence. If a sequence terminates, it's done. It has a spot like, you can't go past that point. If a sequence terminates, it's called a finite sequence. So if it goes forever and ever, it's an infinite sequence. If there comes a point where you're like, I can't keep that pattern going anymore, then it becomes a finite sequence. So for example, consider an auditorium where the seats are arranged according to a specific pattern. There's 22 seats in the first row, so 22 seats, 26 seats in the second row, 30 seats in the third row, so on, so on. So numerically, the sequence is 22, 26, 30. And yes, we could continue that numeric sequence forever, right? It would be infinite. However, in the context of the problem, it does not make sense for the number of seats in each row to increase infinitely. Eventually, the auditorium would run out of space. So suppose that this auditorium can hold a total of 10 rows of seats. Well, then the correct sequence for this problem situation is 22, 26, 30, 34, 38. Again, we're adding on 6 each time. As you can see, 42, pardon me, we're adding on 4 each time. Miss Scott can't count. 42, 46, 50, 54, and 58. But therefore, because of the problem situation, the sequence is a finite sequence. Yeah, we could count by 4s forever, but the auditorium is not forever big. At some point, it's going to run out of space. So we would say it's a finite sequence. And so can you just take a look at this on page 95? Does the pattern shown represent an infinite or finite sequence? And just explain your thinking on that. Go ahead and hit pause, write it down, hit play to check your work. I don't know if you've noticed, but the pattern was we kept taking out the bottom row. Did you notice that? We took out the bottom row, took out the bottom row, took out the bottom row. But there comes a point where there's no more rows for you to take away. So this is a finite sequence. Each stage results by taking away the bottom row of the pyramid until the pyramid no longer exists. At some point, there's no more pyramid. I can't take any more away. So it's a finite sequence as a place where it definitely ends. As always, guys, I hope you found this helpful. I hope you found this useful. If you have questions or concerns, email me, come see me during office hours, come talk to me, and I'll see you guys later. Bye.